Hey, thank you for visiting my channel Kodi Brainy. Today we are going to discuss about data structure. So when I say data structure, it actually focuses on how you can effectively organize your data in an efficiency manner, right? So what I mean efficiency is like in terms of time factor, how quickly or how fast you can process your data. When I say processing your data, meaning there are like various operations that we can perform on a data, right? That's CRUD operations: create, read, update, and delete. So how fast you can perform these operations on a set of data, that is measured in terms of time complexity, right? So how you are going to store the data? There are various different data structure offered by the computer science, right? One of the data structure is a linked list. So today we are focusing on linked list. How a linked list is storing the data, what is the method that this particular list is using to store the data, right? How we can retrieve the data, how we can delete the data from the linked list. All those things will be going through today, right? And then if you look at my screen, you see what I mentioned here is singly linked list. So there are two types of linked list. One is singly linked list and the other is doubly linked list. So when it comes to singly linked list, you see there are different nodes. I put it here. So let us focus on what is a node. Actually, a node is a specific unit, right? If you look at this, the first node, it has two parts, right? The first part holds the data, and the second part, which is indicated by next, that's actually the reference to the next node. Okay, and the head, if you see the head, that is actually, I always consider head as a part of linked list because head always point to the first node in the list. Okay, so that's how a linked list determines the first node, right? Using the head, the list can determine the first node in that list. Once the linked list gets a handle to the first node, then it checks the next reference value, which is actually a reference to the next node. So the list will get to know about the next node by checking the value of the next pointer, right? So it will get the address of the next node and it can jump quite easily to the next node. Then it repeat the process. It's kind of a recursion. And then it can go to the next node by checking the next value and it can jump on other nodes. And it will do that operation till it reaches the end of the node. Okay, if you see the end of the node, you can see the next value is null. This is the end node. The next value is actually null, which indicates this is the end of the node. Now I'm going to a deep dive into more granular details. So let us see what is really stored in the next uh, part of the node. So assume this is my input data, right? 1, 9, and 8. I really want to store 1, 9, and 8 in a linked list. So in order to store in a linked list, what we need to do? We first need to create a node. So I'm going to issue a create node command, right? When I issue a create node command, what is happening behind the scene is depicted here. If you look at the system portion, it's actually the node allocation happens in the heap space. You already know about all the concepts, right? Heap and stack, these are the two memory space which can be located in a RAM, right? So whenever we create a node, it actually the real memory allocation or the memory block allocation takes place in heap area. Who is doing that? The allocator. If you see, memory allocator does that job for us. So whenever we issue a create node command, the allocator gets the user program request and it allocates memory blocks for the new node request. So assume I requested a new node, then it creates memory blocks for the new node here, and it assign a specific memory address to this new node, right? So if you look at here, I just put some dummy value here, MA1. Okay, that's the memory address for the first node. So if you see here, the head will point to that particular memory address, MA1. Okay, so that's why head is able to determine the first node, because head has the reference to MA1 memory location. So it will be able to locate this particular node using MA1 address location. All right, so head got the first node address. Now forget about this part, right? Next part. Now assume I want to store the next data 9. What I need to do? I just need to issue another create node command, right? At that time, what it does is allocator receives the request from you. It allocates memory blocks for this node, and it assigns an address MA3 here, right? So sorry, it allocates an address MA2 here. This is the node request. It allocates MA2 address here. Now what it does is, this is the address, MA2 is the address of this particular node. Now once the address is allocated, what we can do is that the previous node, the first node, next value can be updated to MA2. So when the traversal happen, when the linked list traversal happen, when the journey happens, it starts from the head, it checks the head reference value, then it can get into the first node, and then it checks the next value, which is MA2. Then it can easily determine this particular node in the heap space, MA2. Then it can retrieve the data value 9. The same process happens for the next node. Okay, if this is the, assume I want to store 8, my next data. So I created a node, I put the value 8 here, then there is no node after that because I completed my data storage process. So at that time I can update the next value to null. Okay, so let us iterate back. Traversal is going to happen in linked list. So it first comes here, it checks the head node, it will get the address MA1, so it's able to locate the first node. Then it checks next node value MA2, so it comes here because MA2 is this one, so it gets the value 9, and it checks the next, goes on, next, finally it reaches the end node. How it knows if this is the end node? By checking the value of next. It knows that that's returning a null, which implies that's the end of the node. So the traversal ends there by checking the next value. If next is null, that's the end. Okay, assume if you have only one node, then next will be null, but head will be pointing to the first node. If there is no node, head will be null, there is no next here, right? So that's some of the important concept. Now if I want to delete a node, assume I want to delete 9, what will happen? If I want to delete 9, then this is deleted, right? So right now we deleted that particular node, now the chain breaks, right? Because it's the first node is referencing to MA2, but we deleted actually. So it should refer to 8, right? So the address of 8 is MA3. So the next should be MA3. So now if you see the relationship established, this is what this is how a delete operates. It's just kind of updating the previous node's next value or next point or reference, whatever it is. This is how delete works. Assume we deleted 9, right? Now this is actually unused, right? Because it still resides in heap space. This is actually empty. Now nobody is using, no object is using it, no code is accessing this particular node. It is unused. It is not referenced by anybody. Then this collector is actually a smart guy, right? He's always monitoring unused objects and then reclaims memory and or it can run GC, garbage collection, to clean up the memory, or it can run defragmentation procedures to clean up this. So don't worry about unused space. There is smart guy out there to do all such kind of operations. Okay, so this is the important concept. Now, what is the significance of heap space? The important thing is the heap is kind of a dynamic memory allocation. That's very important. Linked list is working based on dynamic memory allocation. What exactly it means? It means you don't need, the user, you don't need to worry about the memory constraints. You can add as many input you have, right? You don't need to worry about it. Heap will allocate memory blocks for you dynamically. Its memory can grow proportionally based on your needs. So that is dynamic memory allocation. But remember, in the case of array, that's not the case, right? In the case of array, array works in a different manner. You really need to consider the array size when you declare array, right? It's a kind of a sequence of memory blocks when you declare an array. And if the array size exceeded, that's it. It's going to break, right? In Java, you will get array index out of bound exception. Then you are in a need of declaring another array with a greatest size or a greater size or a max size, whatever it is. Then you have to copy values from the previous array. There are a lot of tedious process out there. I'm not going to that direction. Let us come back to the linked list. So linked list is a smart guy compared to array list. Uh, it the specialty of linked list is having a dynamic memory allocation. The heap is a smart guy. Okay. Now the second one is why this linked list is calling. Let me put it back. Why this linked list is called as a singly linked list? By looking into the diagram itself, you can see that the traversal begins from head, and then it moves from one. It moves in one direction, right? It moves in one direction from starting node, from the first node to till the end node. It's unidirectional. That is called singly linked list. It can go only in one direction, starting from the head node, ending at the end node, right? It keeps on moving by checking the next part of the node, and it moves along in the same direction. That's called singly linked list. So I think we covered most of the things associated with the linked list, but let us check the fact sheet of a linked list now. It's the time to check, right? So I'm going to read it out. You just listen what I'm reading. A linked list is a linear data structure where each element is a separate object. Each element, we will call it a node of a list, is comprising of two items, the data and a reference to the next node. The last node has a reference to null. We are talking about this. The entry point into a linked list is called the head of the list. It should be noted that head is not a separate node, but the reference to the first node. That's what I pointed out to you. It's not a node, it's just a reference to the first node. Who is using this reference? The linked list, while traversing, it uses that reference. Now, if the list is empty, then the head is having a null reference, which is true. A linked list is a dynamic data structure. The number of nodes in a list is not fixed and can grow and shrink on demand. Any application which has to deal with an unknown number of objects will need to use a linked list. One disadvantage of linked list against an array is that it does not allow direct access to the individual element. If you want to access a particular item, then you have to start at the head and follow the references until you get to that item. So this particular point is very important, right? In case of array, you can get an item from the array by using the index. But in case of linked list, the cherry pick or random access is not possible. Assume you want to access number 8 from this linked list. You cannot directly go here and pick it up because you don't know the address of this particular node, MA3. That is actually stored in the previous node. You don't know the address of the previous node. That is actually stored here in the previous node, which is the first node. You don't know the address of the first node because the address of the first node is actually handled by head. So in order to access a particular item in a node, the traversal should begin at head, and then from here to here, here to here, once it reaches a designated or a desired node, then only we will be able to retrieve that specific node. So that's what they are telling at this point. One disadvantage of a linked list against an array is that it does not allow direct access to the individual element. If you want to access a particular item, then you have to start at the head and follow the references until you get to that item. So random access or cherry picking is not possible in a linked list. Another disadvantage is that linked list uses more memory compared with an array. We use extra 4 bytes to store a reference to the next node. So if you see here in this memory, you know that node has 2 parts, right? One part stores the data. Assume I want to store, sorry, not I want, I'm storing an integer data type 1, right? So an integer takes 4 bytes of memory blocks, right? Now, apart from that, there is another part which stores the memory reference. That also will take some bytes of memory, right? For additional 4 bytes of memory. So memory consumption is little bit more in linked list when compared to array. Array does not need to store the reference because it uses contiguous memory blocks, right? It uses contiguous memory block. So that's the last point, right? Another disadvantage is it uses more memory. These are all the different and important critical points when it comes to a linked list. Now let us check the time complexity. So I already explained to you, time complexity is something which is related to how long or how long or how much time it will take to process the data, right? So let me try to explain this. Access or search. Accessing or searching an item in a linked list is little bit expensive. By this time, I think you already know that answer. Why it's little bit expensive? Because if I want to access 8, I need to iterate through all these nodes, right? Starting from the head, right? So it needs 1, 2, 3 iterations to reach 8. So if there are n nodes, 1, 2, 3, 4, 5, 6, etc., till up to n, if there are n nodes, it takes n iteration to reach or to get that specific node. That's why the time complexity is measured as big O notation of n, O of n. Okay, it takes n iteration to find a specific node. For search, same thing is applicable, right? But for insertion, I told you, whenever we insert a node, right, all we need to do is just update the next the previous node's next address to the address of the newly created node, that is ma3, right? Assume I created a node here and I put a value 8 here, and then the address, the allocator gives back me address ma3, then I have to update this address here ma3 so that this node can refer to the newly created node. So all I need to do is just update the previous node's next address, right? That's a one operation. That's why the time complexity, big O notation, is O of 1 for the insertion, and deletion also the same thing. It's just a matter of updating the previous node's address or whatever, right? So I hope you got all these concepts. Now, if there is one resource URL here, we got cheatsheet.com. Then if you look at the singly linked list, you can see the access is the time complexity is big O notation O of n, search it's O of n, insertion it's O of 1. So if you see it's highlighted as green, right? Insertion and deletion takes less time. So the green is like good and excellent. O of 1 is, if you look at this chart, O of 1 is at the base, which means it takes less time. O of n is little bit higher in the hierarchy, so it takes fair amount of time to access or search an item in a linked list. For insertion and deletion, it takes a little bit less amount of time to do that operation. So that's all about linked list. So hope you uh, got the point and understand about the linked list. So in my next session, what I'm going to do is, like, I'm going to implement linked list in a Java program. So we can literally visualize what's a linked list and how a node can be created, how we can insert data, how we can point the next pointer to the next node, and then we can basically traverse all these different nodes, and we can output the data. So let us do that in my next session. So please keep tuned to this channel, and thank you for watching my first video.